All right, so now we're going to continue talking about chemistry, and we're going to move on talking a little bit more about water and then introduce pH. So just to remind you about the property of water, so remember a water molecule is two hydrogens bonded with one oxygen atom, and this molecule is a polar molecule. So remember with polar, that means it's an uneven sharing of electrons. So remember, the oxygen is greedy. It's pulling the electrons closer to its nucleus and further away from the hydrogen. And when that happens, we get a partial positive and a partial negative charge. And when we get multiple water molecules together, they can form hydrogen bonds within each other. And I'll show that on the next slide. Now, why is water so important? Well, it makes up a good chunk of your body. 60 to 70% of your body is water. So it has lots of functions. So super important molecule. So why is water so crucial? Well, it does moderate temperature change, and it does absorb a lot of energy before it lets the temperature increase or decrease. Now, it's all thanks to these hydrogen bonds, which are very, very important. That's why the oceans are super, super important. All the energy, solar radiation coming from the sun, the water is absorbing a lot of that heat energy, and it kind of retains a lot of that heat energy. And at night, it's going to release some of that heat energy, and that's going to be trapped in by the atmosphere, and it kind of keeps us in that perfect temperature range that we can survive with life. Now, with the water molecules, they can interact in different ways. So remember we talked about the three stages of matter, where you can have the gas, liquid, and solid. Now with the water, they do form these hydrogen bonds between each of the molecules. So depending, if you keep adding more and more energy to them, the molecules are going to have an increased energy input, and the molecules are going to move a little bit more. So that's when we're with the gaseous state. Think of it that way. Now, when water is in this liquid state, shown right here, or solid state, like an ice in general, it's going to have this very structural lattice structure right here. Now, when it's in this more lattice structure, it actually has a larger surface area, and that does increase into density, and that's why ice does go through and float. Now, another thing about water is it's very cohesive. It's thanks to those hydrogen bonds, and it does increase the surface tension. Now, another key thing about water, it's a universal solvent. So remember when I talked about ionic bonds, I talk about salt, and they're easily dissolved in water. So remember the ionic bonds, it's where the chlorine and the sodium are sharing electrons. So the sodium gave its excess electron to chlorine, and they form this weak bond. Now, what water is going to do, it's going to recognize that and break up that ionic bond. So a few terms, water is a good solvent. It's going to mix with a lot of different things. If you look at this combination right here, we have the solute and the solvent. So water is the solvent. The solute's what's being dissolved. So think of table salt, example. You put the solute and solvent together, and that's going to make your solution. Now, what water is doing, it's going to make what we call these spheres of hydration. So remember, water has that partial negative and partial positive charge. What it's going to do is recognize the overall charge of each atom and kind of track to it. So overall, sodium has a positive charge. So the negative parts of the water molecule are going to surround it. Opposite happening for the chlorine. Now, you know water doesn't mix well with everything. Your oils, your fats are really going to fall in category. These are going to be nonpolar. So remember, nonpolar is equal sharing of electrons. So that no one's being greedy. So it has an overall neutral charge. Now, with molecules that don't mix well with water, they're going to have this term called hydrophobic or water-fearing. They don't want to be with water. The water molecule is going to surround it, but they're not going to be able to infiltrate and actually form any bonds with it. So that's like, example right here with this oil and water image. The bonds between all the different oil molecules are going to be stronger than the bonds the water is trying to create with it. As mentioned, this section is going to be a little bit shorter. Now, water goes through this process called dissociation. So remember, water is an oxygen and two hydrogens, and then they interact with each other, forming these weak hydrogen bonds. Now, these bonds between the hydrogen and oxygen, they're kind of loosey-goosey. They're not totally set in stone. So sometimes what happens is the oxygen will leave one water molecule and join another one. So when that happens, it's called dissociation. So when that happened right here, so we have two water molecules. And what happened is one of the hydrogens left the other molecule. So it forms this molecule called hydronium that has an overall positive charge. And then we're going to have hydroxide, which is just one oxygen and one hydrogen. Now, what's important that this reaction is reversible. So, just because this guy left and joined him right now, he can leave and go back down. So it can go back and forth. And this is what's going to drive our overall pH scale, because we're going to measure how many of these free hydrogens are floating around, and then relative to how much of the hydroxide that we have there. So the pH scale, you've probably heard of it before. It's going to range from 0 to 14. And you'll hear the term acid and bases on there. But basically what we're doing is we're measuring the hydrogen ion concentration. And we're going to measure it in a scale of logs, but we're going to keep it pretty simple right here today. Now at 0, it's going to be called an acid, and this is going to have the highest concentration of free hydrogen ions, so it's going to have a lot of them. Versus the base, which is over at 14, is going to have very few. All right, so lots of hydrogens, hardly any hydrogens in the base area. Now, acids, as I mentioned, have the higher hydrogen concentration. They love to give up their hydrogens and contribute to them. So if you think of acids, you probably think of your lemon juice, vinegar, battery acid. With these, they're going to have a very, very, very tart tasting with them. Versus your bases over here, right there, what they do is they love to find those hydrogens. They have a higher OH level. So what that happens is they love to scoop up free hydrogens. So they're going to be above 7. Water is considered neutral. So that means, we're either giving or taking away these free hydrogens. Everyone's associated and happy. So one of the things I love to watch in class was when you talk about acids and bases is what are many things acid can do. So we know acid is bad. You don't want to consume, especially the really, really low pH acids. So here are 2 videos. They're kind of cool, where they go through and they pour acid on different things and see what it does. So these are just 2 of them. They're for your own entertainment. So please watch them. I think they're kind of fun. You would watch them in class. Now, your body needs to go through and maintain a normal pH. Your blood has to be at a certain level. So there are ways that your body kind of circumvents, like raising and lowering of your pH, and it uses buffers. So a buffer is a weak acid or base that's going to adjust for these changes in pH. So it's going to either absorb these excess hydrogens or hydroxides. So they want to kind of keep it at a neutral reaction. So baking soda is a great buffer. Also think about antacid tablets right there. So, if you have the heartburn, it's starting to come up into your esophagus, you're starting to feel kind of that burning sensation right there because that area is not used to the low pH of the stomach acid. So what the bicarb is doing, are the antacid tablets, and they're going through and absorbing the excess hydrogens and raising the pH to more of the neutral that area can handle. And finally, just want you to appreciate that there's different ways to measure pH. So we would have done this a little bit in lab. There's different ways you can do it. There's actually a pH probe that you can do and actually stick it in solution. It'll give you an accurate number. You can use pH paper, so it's just a strip of paper that you stick into solution, and then it has like a color guide, and you match up the colors to it. There's also using red cabbage juice to actually measure pH. Is kind of fun and unusual. But we would actually done some of this in lab, but I want to introduce it to you. So I'm going to stop this one right there.